All right, so nice job on the homework and the quiz. Let me talk about the quiz first. So, didn't see a lot of issues with the set question, membership table. Everybody did all the columns that they needed to do, which was awesome. So thank you for that. Congruences. So when you're looking for congruences, technically I could say 17 is congruent to 17, and that's a true statement, right? So I could have just copied these down over to the right, and technically that would be true. But when you're asking for a congruence modulo 5, remember we're looking for a number between 0 and say 5 minus 1. So a non-negative number smaller than the moduli. So 17 is 2, 9 is 1. Negative 9, one way to think of that is negative 9 equals something times 4 plus some remainder, right? And we're working mod 4, so we want a remainder between 0 and 3. So negative 9 equals 3 times 4. Sorry. Negative 2, negative 3 times 4 gets me to negative 12 plus 3 left over. Right, for small numbers, one way to do this is just start with negative 9 and keep adding 4. So it's congruent to negative 5. It's congruent to negative 1. It's also congruent to 3. It's also congruent to 7 and so on. So what's the one that we want? It's that one right there. And if you have a bigger number like 17 mod 5, we can subtract 5. Until we get down to something between 0 and 4. So you can noodle around the number that you're starting with and try to get down to something within the range by either adding or subtracting the moduli. So minus 9 is congruent to 3. 10 gazillion and 3 mod 10, right? Remember mod 10 is just the last digit. What's the remainder when you divide this by 10? Well, if that's a 0, that divides evenly by 10, so there's 3 left over. 1 is always congruent to 1 modulo anything. We don't do mod 0. But if you take 1 and you divide it by this horrible number, you get 0 with 1 left over. And then the multiplication we talked about at the end of the quiz, if you were to start to do this longhand, you'll get the least significant digit right away. It's just 7 times 3 is 21. And so that rightmost digit's going to be a 1. That's what you get mod 10. And then the GCD turns out to be 7, and almost everybody got that. A few cases where if you get down to the last step and you find 14 equals 2 times 7 plus 0, a few people grabbed the 2 and said that must be the GCD. Okay, so you always want the remainder from the previous step. But the other thing is you're looking for the GCD of 2, 31, and 35. Once you get an answer, make sure that it is a factor of both of these. That's your first check. And then try to make sure it's the greatest such factor. So if you claim the GCD is 2, you can tell right away there's a problem because neither of these is divisible by 2. But if you divide by 7, 231 divided by 7 goes in 37 times. So 231 equals 7 times 37, and 35 equals 5 times 7. And you know 5 is prime, probably, and 7 is prime. And so the only factors of 35 are 5 and 7, and 5 does not divide 231, so the only possible common factor is 7. And you don't even need to know that 37 is prime, but in fact it is. So that's your GCD right there. But I asked you to do it using Euclid's algorithm. If I do, then you have to actually go through those steps, which I think everybody did. So homework questions, I graded the one using Fermat's Little theorem, which was 7 to the 222 mod 11. I think we did this on the board also before the quiz. Fermat's Little theorem tells you 7 to the 10th is congruent to 1. And then you can take whatever powers you like of this and still get 1. So 7 to the 200th is 7 to the 10th to the 20th. which is going to be 1 to the 20th, which is congruent to 1. And 7 to the 20th is 7 to the 10th squared, which is 1 squared, which is 1. And so 7 to the 222 is 7 to the 20th, sorry, 200th plus 20th plus 2, which is 7 to the 200 times 7 to the 20th times 7 squared. And you found 7 to the 200th is 1. That doesn't take any work. 7 to the 20th is also 1. 7 squared is 49. So this number we're looking for is congruent to 49 mod 11. And so take the remainder. When you divide by 11, it goes in 4 times. That's 44. It leaves you 5 left over. So your answer there is 5. And then the other one I looked at most closely was this this proof. Prove if A divides B and A divides C, then A divides 2B plus 3C. And almost everybody nailed this perfectly. It was so cool to see. So our premise is A divides B and A divides C. Okay, this thing over here, A divides 2B plus 3C, that is not a premise. That's what we're trying to show. Premise are things that we can assume are true because we're asked to show that if these two things are true, then this follows. So how do we do that? We assume these things are true, we apply the laws of logic and algebra, and we try to conclude that this statement is true. So A divides B, that's a premise. A divides C, that's a premise. And then most people use the definition, so if A divides B, that means B equals A times some integer, K1. And that's the definition of divisibility applied to 1. And then since A divides C, C equals A times some possibly different integer, K2. Nobody used the same integer. I was so happy. I was sitting in Pete's. I was like jumping up and down in my seat. People were staring. But it was awesome because everybody used different integers here, which is really, really important. Okay, so that was great. And then you need to somehow make a statement about 2B plus 3C, and most people said, well, let's just substitute these in for B and C and do the following. 2B plus 3C equals 2 times A times K1 plus 3 times A times K2. And that's just substitution of 3 and 4. And then we just do some factoring. 2B plus 3C equals A times 2K1 plus 3K2. And 2K1 plus 3K2 you just observe as an integer. And that's algebra. And then since 2B plus 3C equals A times an integer, we can conclude A divides 2B plus 3C. And that's the definition of divide applied to step 6, and that's what you were trying to show. Good. So this was really good, and the final exam is going to look a lot like the quizzes and the homeworks. So keep doing well on those, and you should be in good shape to do really well on the final exam. Yay. Which is good. That's what we want.
That's why we signed up.
What?
That's why we signed up.
That's why we signed up, yeah. All right. So let me see where we're going. Believe it or not, we're in week 8 right now.
Wow.
So we got 3 weeks left, which for us means a total of 9 classes, and then we're done. Yeah, it's fast. So the 3 topics I'm hoping to cover between now and the end of the quarter is counting, which we're going to talk about this week, and then some graph theory, which we'll talk about next week, and then some automata theory, which is back to state machines, Turing machines, formal languages, all sorts of stuff like that. Automata theory, I think, is one of the funner parts of this course, but it's also something you'll probably take an entire course in as you continue with your CS education. But people I've talked to who have taken this course, say at WSUV, consistently tell me that they really benefited from what they did in 215 with automata theory. So I think it's useful to see it up front and then go into more detail of it later on in another course. So 3 subjects, 3 weeks. We'll see if we can stick to that. So we're going to talk about counting this week. And counting is another one of these things where it seems pretty straightforward. 1, 2, 3, we're done. Okay, so we're going to start from there, and we're going to get into some more powerful concepts and techniques. And your homework that's posted that's due Friday is all about counting. So let me start with something called the product rule. This is a pretty straightforward concept, but it's useful in a lot of different applications. So suppose some task T can be done as a succession of 2 subtasks, T1 followed by T2. So we got some task we want to do. We want to build a school, we want to eat lunch, something. And we can break it down into doing 2 smaller tasks. First you have to do task T1, then you have to do task T2. Okay, if T1 can be done N1 ways, and T2 can be done N2 ways, then T, the original task, can be done N1 times N2 ways. That's the whole product rule. Example, 2 people should sit in a room with 20 desks. So you got an empty room, it has 20 desks in it, and we want 2 people to go into this room and somehow find a seat and sit down. And each person has to sit at a desk, they can't share a desk, and nobody can stand. So how many different ways can these 2 people go into the room and choose where to sit down? When we walk in, how many different situations might we see? So our task T is having 2 people go into a room and sit down. And we're going to break it into 2 subtasks. Task T1 is the task of having 1 person go into the room and take a seat. And then after they've done that, we're going to do task T2, which is having the 2nd person go into the room and take a seat. And if we can figure out how many ways each of those smaller tasks can be done, we can multiply those, find how many ways the original task can be done. So T1, 1 person picks a seat. So how many ways can task T1 be done? I think I heard it. 20. Right? You got an empty room with 20 seats, and you pick someone and you say, hey, go in there and pick a seat and sit down in it, please. There's only 20 possible outcomes of that. And they can sit in the 1st seat, the 2nd seat, the 20th seat, right? So the number of ways T1 can be accomplished is 20. Task T2, 2nd person, picks a seat. How many ways can T2 be done? Right, 19, because there's already 1 person sitting in a seat. So there's only 19 seats to choose from, so task T2 can be accomplished 19 ways. So the product is 380. That's how many ways 2 people can go into a room and sit down. That's the whole product rule. every problem we do with this is going to be exactly like this. Well, not exactly, obviously. The process will be the same. Yeah. Okay, so student IDs. So how many student IDs are possible? Where a student ID looks as follows. It's one letter, A through Z, followed by 2 digits, followed by 1 letter. So instead of 940 blah blah blah, your student IDs look like something like F23Y. And we want to know how many student IDs are possible. What's the largest number of students we can support in our system if that's how a student ID is formed. This is analogous to the question of if my task is to come up with a student ID that matches this, how many ways can I complete that task? So task T, choose or create a student ID. And we're going to split it into 4 subtasks. So Joseph Van, haven't called anyone in a while. So what's a good first subtask to perform?
Pick the first letter.
Pick a letter. Okay, so T1, pick a letter. All right, Jacob, what's a good second task to perform?
Pick a 2-digit number.
Make it simpler than that.
Pick a 1-digit.
Pick a 1-digit number. Pick a digit. Yeah, we really want to pick a 2-digit, but we're gonna stay really lazy. Okay, Cubster.
Pick another digit.
Pick another digit. And then our final subtask, Abe. I don't think Abe's here.
Oh, I'm here.
Oh yeah, you are.
We pick a letter.
Pick a letter, good. All right, if we perform these 4 tasks one after another, we will have chosen a student ID. And any student ID can be gotten by performing these 4 tasks. All right, Derek. Derek's missing out on like the best question of all. This is a really tough one. Damon's not going to get to answer the toughest question of all either. Oscar, so how many letters are there? Is Oscar here? Isaac.
What was the question?
Wrong answer. How many ways can we choose a letter?
Oh, 8.
26. Right, there's 26 possible letters. If our whole task T1 is pick a letter, there's 26 ways you can do that. Right? All right, Justin, how many ways can we pick a digit? Spencer. I need a way to like mark people when they're not here so it doesn't keep calling on them. Munikar.
Here.
Yeah.
9.
Almost.
Oh, 10.
Yeah, so we can do anything from 0 through 9, so there's 10 ways to pick a digit, which means N3 is also 10 and N4 is 26. So how many student IDs are possible? 26 times 10 times 10 times 26.
A lot.
It's a lot, but probably not enough for Clark.
Well, if you don't kick people out, then.
If you don't, yeah, we'll just kick out everybody who's like beyond this number. All right, making sense? And we've been using this rule in some cases without necessarily formally calling it this. Let's think about binary strings. So how many 4-bit strings are there? So my task T is pick a 4-bit string. Right, just some pattern of 4 ones and zeros. And I'm going to break this into 4 subtasks. Task T1 is pick first bit. Task T2 is pick the second bit. Pick the third bit. And pick the fourth bit. Oh, Rachel misses the toughest question of the whole quarter. Ash, how many bits are there?
In a 4-bit string?
No, in just single bit. How many possible bits are there?
In a single bit?
Yeah, I mean, how many values?
2.
2, right? So if we want to pick a bit, we can pick a 0 or we can pick a 1. That's the only choices we have. So the number of ways we can do T1 is 2. The number of ways we can do T2 is 2. And same with T3, and same with T4. So the number of ways that we can pick a 4-bit string is 2 times 2 times 2 times 2, which is writable as 2 to the 4th, which is 16. This is why there are 16 4-bit strings. When you have a truth table with 4 inputs, you have 16 rows. If you write integers with 4 bits, they go from 0 through 15. There's 16 possibilities. And if we generalize this to n-bit strings, we would go down to T sub n, which would be doable 2 ways, and the number of ways would be 2 multiplied by itself n times, which is just 2 to the n. That's another way to see that if you have n bits, you have 2 to the n possible combinations of those bits. 2 to the n rows in your truth table, and so on. How many 4-input logic chips are possible? So we know that there's 4-input NAND gates that we can get from our parts boxes. We know there's a 4-input OR gate that we can buy. How many 4-input gates are there possible if we wanted to make a really big catalog with like every possible 4-input gate being a different part that you could buy from us? How many different gates would there be? So how can we think about this in a way that lets us use the product rule? You got your hand up. What can we think about besides gates?
Input order, bits.
Yeah, keep going, 250. How do we describe the behavior of a gate in 250? Truth tables, right? So we can rephrase this as how many truth tables with 4 inputs. Because any particular logic function is characterized by a truth table, and any truth table characterizes a logic function. It's a one-to-one mapping. So if we know how many truth tables we can write with 4 inputs, that tells us how many 4-input gates we could have. So let's think about a truth table. And you all remember this, right? Right, and here's our output function f. And the behavior of this gate is completely specified by what we put in this column. And if we put in all zeros with a 1 down here, that's a 4-input AND gate. And if we put in 1s everywhere except the first row, that's a 4-input OR gate. If we put in all zeros, that's the NOPE gate that always outputs 0. And we know from the previous question that we have a total of 16 rows. So the question can be reduced to how many ways can we fill in this column with ones and zeros? So how do we break that into subtasks? The task is to fill in this whole column with ones and zeros.
How many one line can you fill? Or what's the one line output you can put in?
Yeah, so how many ways can we fill in this row's output? How many ways can we fill in this row's output? And so on. Right, so we have 16 subtasks. Give me a 1 or a 0, give me a 1 or a 0, give me a 1 or a 0, 16 times, and we've got a whole truth table. And again, the number of ways we can fill in this first entry is 2. The number of ways to fill in the second row is 2. And so on down to the 16th row. And so the total number of ways we can fill this in is just 2 multiplied by itself 16 times, which is 2 to the 16th. So there's 65,536 possible logic gates of 4 inputs. We need bigger parts boxes. And remember the 16, that was the number of rows, right? The number of combinations of these 4 inputs. This was actually 2 to the 4th. So in general, if you have n inputs, you have 2 raised to the quantity 2 to the n functions. So if you have an 8 input gate, there's 2 to the 256th possible 8 input gates. So that's about 10 to the 80th. Number of particles in the universe is 10 to the 79th. So we don't have enough stuff to make all of those even once. All right, still good? So shuffle a deck of 52 cards. How many possible outcomes? So 52 cards, you're going to shuffle it up. You want to know how many possible ways that deck can end up. A lot. Or something, yeah. So how do we get that with the product rule?
Shuffle 51 cards and then go down to
Oh, you're going to be recursive on me. That's an interesting way to do it. How about subtasks?
Task 1, draw 1 card.
Okay. So doesn't matter how we shuffle these as long as it's a reasonable shuffle. So we could actually say, well, when we shuffle, we can think of the following 52 tasks. Pick top card. So which card is going to end up on the top after we're done shuffling? And then pick the second card. Pick the third card. And so on, and at the end pick the 52nd card. So these are subtasks T1 through T53, 52. And to come up with some arrangement of cards in this deck, all we have to do is figure out, well, which card's on top, which one's next, which one's next, which one's on the bottom. So 52 subtasks. So how many ways can we choose a card to go on top of the deck? 52. All right, here's the trickier part. How many ways can we choose the card to go in the second position? Right? We've already taken one card out of our deck and said this is the card that's going on top when we're done shuffling. We've only got 51 cards left. So the number of ways to do task T2 is 51. Number of ways to do task T3 is 50. And when we get down to choosing what the last card is to put in the deck, we've only got one card that's not in the deck yet. that's the card we've got to pick. So the number of ways to do task 52 is 1. So the number of ways to do the whole thing is 52 times 51, all the way down to 1, which we write as 52 factorial. So this is why factorials always pop into these kinds of things. Yeah.
There's a fun fact about the possible combinations of a 52-card deck.
Mm-hmm.
There's so many possible combinations that every time you shuffle a deck, there's a good chance. I think it's most likely that no deck of cards has ever been in that order.
Yeah, that's cool.
It's 8 times 10 to the 67.
That's pretty cool. You know what bothers me about shuffling cards? You shuffle a deck of cards, right? Really shuffle it up really good, shuffle it for an hour. And then look at the arrangement of cards. What's the probability that that was the way that the cards came out? It's like almost 0. Every single time I shuffle this deck of cards and it comes up with a combination that was almost guaranteed never to happen, and it did. Every single time. That bothers me.
It's like a reverse lottery.
Yeah. Oh, I figured out how to win the lottery. I don't know if I should tell you because you'll make me share it with you. I have a knack for picking lottery tickets with no winning numbers every single time, 0 numbers. Right? I pick 6, and there's no winners on them, right? So I'm going to pretend that I pick like 11 tickets. I'm going to write down the numbers I would pick, and I know none of those will come up, and the only numbers I didn't pick, those have to be the ones that come up. So I'm going to do this Wednesday, and if I don't show up the next day, you'll know it worked.
But you'll subsequently have to pick those numbers.
No, I'll give them to my cat and let my cat pick them. That'll be the loophole. I'll have to get a cat first. It gets complicated.
It's a long-term process.
Yeah.
You gotta put in the work to get where you are.
All right, just for kicks, let's go back to our student IDs. And suppose that we're doing the same thing, but we have a new requirement that every character has to be unique. So we can't use the same letter twice, and we can't use the same digits twice. Is that significantly harder to solve this question for?
No, could you just decrease those numbers?
Yeah.
Yeah, so we can still pick the first letter 26 ways, we can pick the first digit 10 ways, but now to pick the second digit, we only have 9 choices because we can't reuse the digit we picked for task T2, so this becomes 9. And to pick a letter, we can't reuse the same letter we did for task 1, so now we have only 25 possibilities. So now the total number of ways we can pick a student ID is 26 times 10 times 9 times 25. It's the same process, just slightly different calculation. Okay, let's do some math. Suppose f is a function going from set m to set n. And suppose the number of elements in set m is little m, and the number of elements in set n is little n. So these are finite sets. How many functions are possible? That's horrible grammar. But the correct grammar would be something like, what's the total number of functions from m to n that we can come up with, or something like that. But how many different ways could we define a function from m to n? So let's try to break this idea of coming up with a function down into subtasks. So what is a function, first of all? We talked about this briefly. What do we mean when we say a function from m to n?
It maps inputs n, outputs n.
Okay, so f maps elements of big M to elements of big N. So for any element in M, we assign some particular element in n, which we say is what f maps that element in M to. So, squiggly bubble picture. There's M, there's N. Here's a point in F, in M. Here's a point in N. F does that mapping. So how can we define a possible function from M to N? What do we have to do to define a function?
Each subtask would be taking one element from M and all the possible combinations in N.
So we can do this as a series of tasks. T1, map first. Sets are unordered, but it's a finite collection, so let's just assume some ordering on these elements. So take the first element in M, map the first element of M to something in set N. Task T2, map the second element of M to something in N, and so on. And we have a total of little m elements to map, so task T little m says map the mth element of M to something in N. If we complete those M tasks, we've defined our function, because we've said what every element in the set M maps to. Okay, so we're just thinking about task T1. I've got a particular element in mind. I've got this element right here. My task is to say, what does this map to in N? Does it map here? Does it map here? Does it map there? Does it map here? Does it map up there? So how many ways could I answer that question? What is this element going to map to in N? Say it.
I want to say N.
Yeah, right? So the number of ways I can complete task N1 is just little n, because that's how many elements I have over here. If N has 5 elements, my task T1 says, okay, I'm going to map it to either this first element, second, third, fourth, or fifth element. So the number of ways to do T1 is little n. And if I don't put any restrictions on what can map how many times to other things, right, the number of ways I can do task T2 is also n. And the number of ways I can do task T sub m is also n. So the total number of ways I can come up with a function is n times n, a total of m times, which is n raised to the power m. In our case of logic gates, we were mapping from, so we had a 4-input logic gate, so we had 16 values over here, we had 2 values over here. So little n was 2, little m was 16, 2 to the 16, that's the number of possible functions. All right, so this is just a general case of what we already did with logic gates.
So just, I think just depends on how many elements in M and N.
Mm-hmm.
So if M has just one element, so we have to one way.
If M just had one element?
Yeah.
Yeah, so if M has one element, then we have a total of n possible functions.
M have one element and N have one element too.
If they both have one element, there's only one possible function. And if n only has one element, even if there's 100 things over here in M, there's only one possible function, because everything's got to map to that one element in N. So it's going to be 1 to the M, which is just going to be 1. And I always recommend doing what we just did, right? Try some particular cases with this and see if it makes sense. And if it doesn't and you didn't make any mistakes, then you found a hole in like mathematics, which is good. You get bonus points for that. Extra credit, yeah. Okay, we'll take a break after this one. What if this function has to be injective? Oh boy, now we got to remember what injective means. So what is injective? Say again? Surjective is onto. Injective is something else. One-to-one. So injective means that we can't have two things mapping to the same point. Everything has to map to a different point over here. So an injective function, every arrow has to go to a different spot over here in N. So if we make this injective, well, function T1, task T1 is picking some first element, mapping it. That can go anywhere, right? So there's still N ways that we can satisfy task T1. T2 says, take your second point and map it into N. Well, it can't go to the same point that T1 went to. So we've only got N minus 1 possibilities. So N2 is little n minus 1. N3 is little n minus 2. And N sub m is n minus, and this is going to end up being m minus 1. And so the product of these will tell you how many injective functions there are. And it's a fair bit smaller than n to the m. Make sense? All right. So let's take a 5-minute break, and we'll finish up product rule, and we'll talk about sum rule. SUM, not SOME.